Nothing beats. In this video, we are going to look at several different applications of related rates. Now, just keep in mind, we're going to look at a few examples here. However, there are really endless examples of this. So this is just to get exposed to a few different situations in which related rates are in the situation, and also kind of develop a few strategies of tackling these problems. So let's get going here. Okay. So like I said, there's many applications involving related rates. I'm just going to take a look at a couple here. So, and as I said, we're going to look at a couple examples and just think about general strategies dealing with such situations. Here is the first situation. Let's suppose that we have a square, just a square chilling, and the side length of the square is x, whatever that might be. Let's further assume that the size of the square is changing, and it is increasing the size of the square based on the fact that dx dt is equal to 3 centimeters per second. So you think x is the side length of the square, and that side of the square, of course squares have all equal sides, so all of the sides are increasing at a rate of 3 centimeters per second. And so we can kind of get a visualization of this, right? I have a diagram here that I'm going to show you. So here is just some square, and I just put it in the coordinate plane here as you see in the picture. Just think of x in this direction. However, all of the sides here are the same value x because it's a square. And I can increase my x, and as x gets bigger, the size of the square gets bigger. Right? That's what we're talking about here. Some situation as time goes by, the sides of the square are changing, they're getting bigger, and other things are also changing. So in this first example, what we'd like to take a look at is ask some questions about how is other things changing. So for instance, in part A here of this problem, just think, at what rate is the area of the square? So we want to know how fast is this area of the square changing when the sides of the square are 4 centimeters long. Keeping in mind that we're assuming that the sides of the square are increasing at a rate of 3 centimeters per second. So if you go back to this picture here, you think, oh, if the side lengths of the square increasing at a rate of 3 centimeters per second, right? These sides, they're getting bigger, 3 centimeters per second. Then how is the area changing as the side lengths are changing at that rate? We should be able to say something about how much the area is changing as we increase the lengths of the sides. And that's what this question is asking us to do. So in order to do this, we must first ask ourselves what it is that we're looking for here. We're asked to find the rate at which the area of the square is changing. So we could think of, this area here that we're looking for. How is the area changing as time is changing? Keeping in mind that our value of x is changing with time, right? So as we saw in the previous video, we have this situation in which multiple quantities are changing as time goes by. And we know that because we're given this information right here, right? dx dt. How fast is the side length changing as time goes by? And that is in 3 centimeters per second, right? Per unit of time. So if we keep this in mind, we're going to look for dA dt here. How is the area changing as time goes by, given that x is a function of t as well? So what we always want to do when dealing with a related rates application like this situation is, first, we'd like to come up with an equation that relates the variables that we have in the situation. In this case, we're dealing with area and in terms of the side length x of this square. So it seems fitting to have the correspondence between the two variables. A is equal to x squared, right? Because that's the area of the square. And it also relates with two different variables of concern, the area and the side length of square x. Now from here, of course, we are interested in finding dA dt. So to do that, let's go ahead and differentiate both sides of the equation with respect to t. So d dt of a is d dt of x squared, remembering to keep in mind that x is a function of t, so we'll need chain rule there. On the left side, we just get dA dt is equal to, well, derivative of x squared, where x is x of t, chain rule, 2 times that x, power rule, times the derivative of the inner function, dx dt. And from here, we have the formula that we're looking for. How does the area change as time goes by? Well, it's 2 times the value of that side length x times the rate of change, dx dt. So that's the general situation, and we want to know what happens when x is equal to 4 centimeters. So now that we know that at this certain point in time, right, we're changing this size of the square as time goes by, it's getting bigger in size. Take a snapshot. When the side length is 4 centimeters, if the side lengths are changing at a rate of 3 centimeters per second, then at that instant in time, how fast is the area changing? And so we can say when we have that x is 4 centimeters, and of course we also have that dx dt is equal to 3 centimeters per second, then what's the result? Well, then dA dt at that moment is going to be 2 times the x, which is times 4 centimeters, right, times 3, which is dx dt, centimeters per second. So if you think of the units here, we have centimeters squared per second. So units are important here to keep track of things that are going on. I got x is 4 centimeters, dx dt is 3 centimeters per second, so the units come out to square centimeters per second, which they should, because it's the rate of change of the area here. And in the end, you multiply that out, 8 times 3, that's 24 square centimeters per second. And there's our first little part of this problem. And as you can see, we set up the problem. You got to dissect it, set up your variables, find an equation which relates the variables, keeping in mind that the variables are changing with t, time, and then find what you're looking through by using implicit differentiation with respect to t. Just another quick one, another evaluation type of problem, really. At what rate is the area of the square changing when the sides of the square are 8 centimeters long? So really, this is no different than what's above. The only difference is now we have that x is 8 centimeters. So all we're going to do is we'll say at this moment, right, and that is when the side length of the square is 8 centimeters, and we're still assuming that dx dt is 3 centimeters per second, then it follows that dA dt, remember right above, 2x times dx dt is going to be 2 times x, 8 times 3 dx dt, which is a 24 times a 2, 8 times 3, 24 times a 2, which is a 48 square centimeters per second. And there's our first example. All right, so let's look at another example here. Let's suppose this time we have a spherical beach ball. Got a spherical beach ball, fun. And it's being pumped up so that its volume is increasing at a rate of 120 cubic centimeters per second. Our first question is, how fast is the radius of the ball increasing when the diameter of the ball is 30 centimeters. So again, let's take a look at a little diagram representing the situation. And here we have our little beach ball. We need to make it bigger so it's more pumped up. You can just see the 3D kind of situation going on here. I put some points on the edges so we see that's the edges of the beach ball in our three-dimensional picture. And so as I increase the R value here, this is my radius, we could see the beach ball is getting bigger. Now, we have the situation in which the volume of the beach ball is changing, right? It is changing at a rate of 120 cubic centimeters per second. So you just imagine it's being pumped up at that constant rate. And the beach ball is growing in size. And when it does, its volume is changing, but correspondingly, its radius is also changing at some particular rate. Now, in part A here, like we already said, we'd like to know how fast the radius is increasing when the diameter of the ball is 30 centimeters. Now, of course, instantly we could say, okay, if the diameter is 30 centimeters, then the radius must be 15 centimeters, right? Because that's half the diameter. And now we need a relationship between our variables. Now, we have the variable r here. We're asking questions about that, right? The radius, let's just assume that it's the variable r here. And when the radius is 15 centimeters, we need a relationship between the radius and what's given, and that is dv dt, if you will, the rate of change of volume with respect to time, is 120 cubic centimeters per second. So really we're looking for a relationship between v and r. Now, we know that relationship, and that is the volume of a sphere is 4/3 pi r cubed. And from here, we can find the relationship between the derivatives, the related rate that comes from this. And that is, let's go ahead and just, again, differentiate both sides of this equation with respect to t. So d dt of v is derivative with respect to t of 4/3 pi r cubed. Now on the left-hand side, we just get dv dt here. And on the right-hand side, keeping in mind that the radius is changing with time, right? So the radius is also a function of t here. And as I differentiate the right-hand side, I'm going to get a situation that, again, involves the chain rule. And that is power rule first, 4/3 pi, bring down to 3, lower the power by 1, and then times the derivative of that inner function, which is the derivative of r with respect to t. Cleaning up this right-hand side a little bit, we get, of course, that these 3's cancel, and it's just 4 pi r squared times dr dt. Now, in this situation, we're trying to find, at some moment in time, what dr dt actually is. Right? How fast is the radius of the ball increasing when the diameter of the ball is 30 centimeters or when the radius is 15 centimeters? How fast is the radius of the ball increasing? We're trying to find dr dt here at this situation. So, in this instant, we can find this by first, of course, isolating dr dt. So dr dt here over on the left, if I just divide both sides of that equation by 4 pi r squared, I get that dr dt is 1 over 4 pi r squared times dv dt. And now I can plug in the information we know. So at this moment, and that is the moment in which r is 15 centimeters, and we know that right above, dv dt is constant at 120 cubic centimeters per second. Then we get at this moment, dr dt is going to be equal to 1 divided by 4 times pi times r, that's a 15, and keeping in mind that's centimeters being squared here, times dv dt, which is 120 cubic centimeters per second. So on top we got cubic centimeters per second. In the denominator we got square centimeters. So see the unit analysis here, we will be left with units of centimeters per second, which is exactly what we need. And if you just multiply that all out, it ends up that you get that this is equal to 2 divided by 15 pi centimeters per second. So you could press some buttons to see how much that is approximately, but that's how fast the radius of the ball is changing or increasing when you have that the radius is 15 centimeters and the volume is changing at a rate of 120 cubic centimeters per second. Now there's a part B here. Assuming that the ball is still increasing in volume at a rate of 120 cubic centimeters per second, let's figure out how fast now the surface area of the ball is increasing when the diameter is 40 centimeters. Now again, we know that if the diameter is 40 centimeters, that also means that the radius is going to be 20 centimeters. All right. Now, the difference here is we are now asking a question in which the surface area is changing. So we must recall that the surface area of a sphere is 4 pi r squared. And so we'd like to relate the rate of change of the surface area, ds dt, with the rate of change of the radius, dr dt. So again, we'll go ahead and differentiate both sides here with respect to t, giving us ds dt is equal to derivative with respect to t of 4 pi r squared, still keeping in mind that the radius is a function of t here, it's changing. And so from here, we get ds dt is equal to, another general power rule situation, 8 pi times r times the derivative of that inner function, dr dt. Now we know at this instant r is going to be 20 centimeters, but we have to be a little careful here now because dr dt, that's also changing. Now in the previous example, we found what the value of dr dt was when r was 15 centimeters. However, this is now a situation in which the radius is 20 centimeters. So in order to figure out what the rate of change of the surface area is at this moment, we're going to have to recalculate what dr dt is when the radius is now 20 centimeters rather than the previous situation, which was, of course, 15 centimeters. So we know the formula for dr dt. We know that dr dt is going to be from the result we got above, 1 over 4 pi r squared times dv dt, right? And so we're going to go ahead and say, well, at this moment, when r is now 20 centimeters, we get that dr dt is going to be equal to 1 divided by 4 times pi, but now times 20 centimeters squared, times dv dt, which we're still assuming to be 120. And if you go ahead and just press some buttons and simplify that, that ends up being 3 divided by 40 pi, and that's in terms of centimeters per second, of course. So there's my dr dt at this moment, and we know that r is 20 centimeters, and thus we can go ahead and plug that in to the formula that we just found, this formula right there. And what follows is, well, therefore, again, at this moment, the rate of change of the surface area of this beach ball, how is the surface area changing, is going to be 8 times pi times r is 20 centimeters, times 3 over 40 pi, and that's in centimeters per second. So again, we see that this is going to be a square centimeters per second units. And when you press the buttons, this ends up coming out to a nice number, 12 square centimeters per second. So the surface area is increasing at that particular instantaneous rate at this particular moment. And there's another example of a related rate. Now I got one more example here to do in this video, and this one will be a little more involved than these previous two, I think. So let's take a look. Let's dissect this last situation here. There's a woman who owns a house, and she has a strangely shaped swimming pool in her yard. It has the shape of an inverted circular cone with a base radius of 8 feet and a depth of 16 feet. Now, this pool was recently drained for cleaning and is now ready to be filled back up. Water is being pumped into the pool at a rate of 8 cubic feet per second. The question is, how fast is the water level rising when the depth of the water is 9 feet? Okay, so there's a lot going on here, right? First thing we might want to do is just draw a little picture. So here's my base of my cone, and then here's my cone. In this case, an inverted circular cone. So, you jump in right there into the water, it goes splash, and that's what the pool looks like. The base radius is fixed, right? We know that this base radius right here is 8 feet. We also know the depth. The depth of this pool, that amount, is 16 feet. Okay, so that's what our situation is. That's the shape of her pool. Those are the dimensions of the pool. And so another picture here, just to visualize, here's her pool with those dimensions, and I'm just using H here to represent the height of the water from the bottom, and we're pumping the water into the pool, right? So as we pump the water into the pool, then of course the volume is changing. However, if we notice, both the depth that we're at right here and the radius of the corresponding amount of water that's in there, it's kind of like a mini cone, it's also changing, right? So as the volume increases, both of those dimensions are changing as we keep pumping water into the pool. And we'd like to know at some instant, how fast is that water level rising when the depth of that water is 9 feet? So that's that particular instant. Okay, so some particular instant here is, we just saw the water level is going to be changing. And here's my water. There it is, yeah. And so, the question is, how fast is that water level changing, the height of the water, if you will, at this particular moment? So we have a few things here that we know, right? We know that the water is being pumped into the pool at a rate of 8 cubic feet per second. So that's a dV dt, right? My rate of change of my volume of water is 8 cubic feet per second. We know that. Now let's name some variables here. Sometimes we just got to name some stuff. Let's call the height of the water, or the depth, if you will, right? The water level. Let's call that the variable h, like I was using in that other diagram. And then let's call the corresponding radius of this little mini cone within the cone. Let's call that base radius r. So you notice here that both h is a function of t and r is a function of t, and they are both changing as the volume, of course, is changing. Now, we know that the volume of a cone can be given by 1/3 times pi times r squared h. This is an established formula. And at first glance, it may seem reasonable to say, let's go ahead and differentiate both sides with respect to t here. So let's just see what happens when we do that. So if I differentiate the right side, I'm going to get a ddt of 1/3 pi r squared h. Now r and h are both functions of t, so this is a product rule situation. That's a 1/3 pi times derivative of h with respect to t times r squared, so r squared times dh dt, and then plus an h times chain rule again on r squared, which is a 2r times a dr dt. And nothing's incorrect about that. That is the formula. However, what we're looking for, right, what our goal here is at this moment to figure out what is dH dt, right? And so if I were to try to isolate the dH dt here, right, how fast is that water level rising as time goes by, I would have to know many things. I'd have to know the rate of change of the volume with respect to time, which we know. I'd also have to know at that moment the value of R and the value of H, and also dr dt. And so we don't have any information about dr dt. And that means we're going to have to come up with something else here. If we could eliminate the variable R altogether from the get-go, then we would just have an equation here for the volume of the cone that relates the volume with the height or water level of the water. And so we go back to our picture here on the left. And so that's what we need to do. Is there a relationship between H and R so that I can eliminate the R altogether? And in this picture here, you see there's some symmetry going on. You see the little triangle that is formed within the cone, both the big triangle and the red triangle. And oftentimes in a related rates problem, there is some underlying geometric properties going on between the variables. And so here that's one of those situations in which we don't have enough information to figure out what dH dt is right over here. So if we somehow found a relationship between H and R and redifferentiated, we could come up with that answer that we're looking for, that relationship between V and H. So remember, similar triangles, that's what we're going to use here. By similar triangles, we're going to get some information. So similar triangles tells us that, remember, the sides of similar triangles are proportional to each other, those ratios of those sides. We get that, if you will, just picking this particular proportion, the little radius, which is that little side of that little triangle, over the big radius, 8, corresponding side of the big triangle, is equal to the value H, the height of that little triangle, divided by the big H, if you will, which we know is 16. And thus, we can see here that if I just multiply both sides by 8, I get R is a half H. So at any given moment, R and H are related through this equation. And what that allows me to do is rewrite the volume. So my volume, which was 1/3 pi r squared h, well, now I can replace the r with a half h. So this is a 1/3 pi times a 1/2 h squared times an h. And if you multiply that all out, you're going to get a 1/12 pi h cubed. And thus, we now have the relationship between the volume and the water level H, as we're calling it here. And thus, since I'm looking for dH dt, I go ahead again, differentiate both sides. So left-hand side dV dt, right-hand side differentiate with respect to t, 1/12 pi h cubed, which, remember, h is a function of t here. So I'm going to get 3 comes down. That's going to give me a 1/4 pi h squared, but then times dH dt. And now I can solve for dH dt to get that dH dt in general is going to be, well, just divide both sides by 1/4 pi h squared, or equivalently 4 divided by pi h squared times my dV dt. So that's always the situation. Now, the moment that we're looking for, remember, is water level 9 feet. That's my H, right? And then we know that dV dt is 8 cubic feet per second. So I'm going to go ahead and just plug in those values down here. So at this moment of concern, at this moment, we get that dH dt is going to be 4 divided by pi times h squared, so that's times a 9 squared, 9 feet squared, times dv dt, so dv dt was 8 cubic feet per second. And when you multiply this out, you get 32 feet over 81 pi seconds, if you will, or 32 feet per second over 81 pi. Probably said that a little strangely. 32 divided by 81 pi feet per second. And in fact, if you press a button, that's about 0.1257 feet per second. And there you go. That is the answer to this particular situation. And as we can see in this last one, we had to do a little bit more work. And sometimes this is needed. You might need to find a relationship between two of the variables, if there's more than two variables like there was here, right? V, R, and H. And maybe you'll need to find a relationship between two of them, replace that in our original relationship between the variables so that we form a situation in which we only have two variables and we can find the information we're looking for. We also use some geometry in this problem to help us do that, which is not uncommon. But there you go. There is some examples of applications of related rates, and there's so many more, but hopefully this will give you a decent strategy in tackling other problems that you may go and attempt. That's it. Until the next video, it's Math and Beats, and I'm out of here.